Lesson 10.1.1 Introduction to the chi-square test statistic. Manufacturing cereal. In a previous lesson, you designed a children's cereal that struck an effective nutritional balance to receive a favorable rating from Consumer Reports magazine. In this lesson, you will think about how to produce a cereal that can be successfully marketed to consumers. Effective marketing helps keep costs low while increasing sales and profits. Because of manufacturing costs and concerns, all the cereal pieces in the cereal that you develop will be the same size, shape, and weight. It is expensive to make cereal in many different shapes. However, suppose that research shows that certain colors and distributions of colors are more appealing to consumers. Different colors are inexpensive to produce. Assume that the desired color distribution for the cereal is 20% red, 35% white, and 45% blue. Your cereal manufacturer claims that the cereal is being produced according to the desired color distribution. To check this claim, you take a simple random sample of 1,000 cereal pieces and count how many of each color are present in the sample. When the sample provides strong evidence against the claim that the population proportions are 20% red, 35% white, and 45% blue, this implies that something may be wrong with the production process. Try these. Number 1, how many pieces of each color would you expect in your sample of 1,000 pieces if the true population proportions were in fact 20% red, 35% white, and 45% blue? Note, these three expected counts should add up to 1,000 since you have 1,000 pieces in your sample. Up in the middle of the page where it says language tip, they point out that a category's expected count is the number of observations in the category if the distribution of proportions in the sample follows a hypothesized distribution. So they've hypothesized what they are after. They're after 20% red, 35% white, and 45% blue. So if we have a sample of 1,000 pieces, we would expect 20% of 1,000 to be red. We would also expect 35% of 1,000 to be white, and then we would also expect 45% of 1,000 to be blue. So how do we find percentages of an amount? That just involves multiplication. So if you want to find 20% of 1,000, that's 0.20 times 1,000, and when you multiply that, you're going to get 200. So you would expect 200 red pieces. For the number of white, you would have 35%, which is 0.35, and then you're going to multiply that by 1,000, and that would be 350. And then for 45% blue, that would be 0.45 times 1,000, and that would be 450. And if you add up those expected counts, you get back to 1,000. And you can also notice while you're here, what do you get when you add up 20% plus 35% plus 45%? You get 100%. Okay, so now moving on to number 2, if you obtained a sample of 1,000 pieces that exactly matched the 3 counts you just computed in question 1, it would suggest that there are no problems in the manufacturing process, since your actual counts were the same as your expected counts. Recall that you have discussed sampling variability in a previous module. You know that it is unusual to obtain a sample with the exact counts that we just computed in question 1. So question A. For a sample of 1,000 pieces, give another example of counts for red, white, and blue pieces that would suggest that there are no problems in the manufacturing process. So again, if there are no problems in the manufacturing process, that would mean that the actual counts were the same. Question A is asking, well, what if there was something a little bit different? Could we have something that seems to still say that there's no problems in the manufacturing process? Like if you expect to have 450 blue pieces, could you tell if there were really just 449 pieces that was different from 450? At a glance, you probably couldn't tell. So what if we had 449 blue pieces? So we took one away from 450, so we still want these numbers to add up to 1,000. So what if I add one to 350? So 351. But then my number of red pieces still stays the same as 200. Notice if you take a minute and add those three numbers I just wrote in part A, they still add up to 1,000. But we can't really tell the difference between what I wrote here in part A with what we expect from number 1. So that's pretty close. So what you might want to think of as a way to interpret part A is it's close to what is expected. And if you want to think about it, we do this in everyday life. You go buy a bag of chips. Do you sit there and count the number of chips? Or is it just kind of feel the same as when you bought that same bag of chips the last time? So it's close enough. This is the same idea. But now how about part B? For a sample of 1,000 pieces, give an example of counts for red, white, and blue pieces that would suggest that there are some problems in the manufacturing process. This means it should be far from what is expected. So there's lots of options for both of these. Like, what if every single piece was red? 1,000 red. That would mean I'd have 0 white and 0 blue. That would be pretty far from what was expected. You can be creative and think of other options for this, of what seems to be close or what seems to be far from what's expected. But we're going to do another couple examples that'll do the same thing in just a little bit. Number 3. The tables that follow show the distributions of 4 random samples. Each sample has a size of 1,000 and is taken from 4 different production days. For each sample, carry out the following 3 steps. First, examine the table containing the distribution of the actual counts obtained from the sample. Then decide whether you think the sample provides strong evidence, moderate evidence, or weak evidence against the claim that the population proportions are 20% red, 35% white, and 45% blue. So we're looking for evidence against that claim. And we just want to know if the evidence is strong, moderate, or weak. Record your response in the space provided. And then finally, list the characteristics of the sample that led you to your decision. So first, part A, day 1 sample. In that sample, we have 210 red, 360 white, and 430 blue. And what they have in the table below is a comparison of what we just observed in the sample. So that's the observed data. And then in the last row, we have what's expected. That came from number 1. So here we have observed 210 red when there should have been 200. We've observed 360 white when there should have been 350. And then we've observed 430 blue when there should have been 450. So on the next page, it appears that the day 1 sample provides, and we need to circle one of these here. So if we want to think if it was strong evidence against the claim that the proportions should be what we expected, 200 red, 350 white, and 450 blue, if it was strong evidence, then we should see what we observed to be pretty far. But these don't seem to be pretty far. 210 versus 200, or even more so, 430 versus 450. That might be hard to tell the difference between that. So I don't think that we would say strong evidence or even moderate. This seems just like our first example from question 2. This seems to be pretty weak evidence against the claim that the population proportions should be 20% red, 35% white, and 45% blue. As a reasoning, we could say they are all pretty close to what was expected, and we can even be more specific and say all within 20 of what's expected. Where did I get 20 from? The difference between the observed blue and the expected blue is 20. The other two colors are within 10. So we've got some small differences. If you're not sure about that, as we go through the next couple days, for day 2 sample, day 3, and day 4, you might see some clearer differences. So now, how about part B, the day 2 sample? Here the number of red is 200. That's good, that's what's expected. But the number of white is 425, and the number of blue is 375. So now here, how about we take a look at the difference? What's the difference in the observed and expected for blue? If you take 450 minus 375, this is off by 75. And the same thing is happening with the white. Those are off by 75. So those two colors are drastically different from what should be expected. And notice it's much more drastic than what we saw in part A. So here, even though the red colors are the same, the white and the blue are off by a lot. So we might say that this is strong evidence against the claim that the population proportions are 20% red, 35% white, and 45% blue. And why would we say that? We could say that the white and blue counts are both off by 75. All right, now part C. Here's a third sample, day 3 sample. The red is 180, the white is 460, and the blue is 460. So here notice that the red is off by 20 between the observed and expected, but the white and the blue, those are both off by 10. This is similar to the day 1 sample, right? Where we had one color was off by 20, but the other two were off by 10. So we would probably say the same thing as we said then. This seems to be weak evidence against the claim that the population proportions should be 20% red, 35% white, and 45% blue. And the reason why that we would say is, again, sort of like what we said for day 1. The counts in the observations are off by at most 20. So again, if you compare this to day 2, where they were off by 75, this seems different from that. And then finally, part D, day 4 sample. Here the red is 235, the white is 355, and the blue is 410. So now if you compare what's observed to what's expected, the red has 35 more in what's observed, the white has 5 more, but the blue has 40 less. So this isn't as extreme as the day 2 sample, but this also isn't as small as what we saw in days 1 and 3. So we might say that this is moderate evidence. It's kind of unsure. Could be strong, could be weak, somewhere in between. And the reason why we might say moderate, again, we could just point to the samples that we have. We could say that red and blue are off by about 40. The red is off by 35. The blue is off by 40. Those are both about 40. And you can see that's somewhere in between 20 and 75, the numbers we were using on the previous days. So that's why we're saying that the evidence is moderate. So question number 3 was really just giving us a little bit of an introduction to this idea of comparing samples. But we're going to need to be a little bit more intense with this and have some stricter way of determining what's strong or weak evidence. So we're going to start to see that as we move into the next set of problems. So question 4. Based on your work in question 3, which sample provides the strongest evidence against the claim that the population proportions are 20% red, 35% white, and 45% blue? What characteristics of the sample influenced your decision? So here, just summarizing, we said day 2. And the reason why we said that was because the white and blue were both off by 75. So then number 5. Sometimes in production, you may not find 20% red, 35% white, and 45% blue as you had expected. When might you become concerned about a large difference? Would you be concerned if an actual sample count differed from its expected count by about 10 pieces? How about by 50 pieces or 100 pieces? This is really an opinion, but again, you want to think, is it close enough, or is it starting to get pretty far from what we expect? 10 pieces, probably not concerned. Maybe if it's off by about 50 or 100 pieces, maybe a little more concerned. Number 6, it would be useful to have a statistical measure of deviation. A statistical measure of deviation could help you decide how much the distribution of a sample, such as those shown previously, deviates from what is expected. Create a method and/or statistic to measure which sample deviates the most from the ideal expected distribution. To help us with this, I'm going to ask us just to remind ourselves when we saw deviation before. And also that deviation also related to difference. So maybe think we saw standard deviation all the way back in Module 2. And that involved taking some differences. And then you also might remember that you took those differences and you squared them. Squared differences is something that we could consider. And if you go back to what I was looking at in our observations versus expectations, I was finding differences. So, what if we looked at the squared differences of observations, so observed, minus what's expected? So that's what we're going to start to look at next. Quantifying the strength of the evidence. Earlier in this lesson, we talked about strong evidence against a claim about population proportions. Strong evidence against the claim that the population proportions are 20% red, 35% white, and 45% blue implies that something may be wrong with the production process. For each sample, you can compute a chi-square statistic. The chi-square statistic is useful in assessing the strength of your evidence that something might be wrong with the production process. The chi-square statistic is a measure of deviation that utilizes the difference between an observed count in a given category and the expected count for that category. Keep this information in mind. In this module, you will learn how to use the chi-square statistic in different types of chi-square tests. This will be similar to the way you used z-scores for testing hypotheses in previous modules. Off to the right, here's the language tip for how I am pronouncing this phrase, chi-square. Chi is a Greek letter pronounced chi, ki phonetically as in the word kite. The symbol for a chi-square value looks like an x with a squared. You're going to probably see me write it like this, where I give a little bit of a curve to one part of the x, so I can tell the difference between it and the letter x. And then I have the exponent of 2 for chi-squared. So you need to know. The steps for computing a chi-square statistic are as follows. 1. For each category, compute the difference between the actual count for that category obtained from the sample and the expected count for that category. Number 2, for each category, compute the square of the difference obtained in step 1. So here's the square difference that I was talking about. Step 3, for each category, divide the square difference obtained in step 2 by the expected count for the category. So this is just like in standard deviation, we took a square difference and then we divided it. And then step 4, add up the step 3 calculation results from each category. That will be the chi-square value. So for example, using the day 1 sample data set, here they have the observed counts, 210 red, 360 white, 430 blue. Then the expected counts, that came from number 1, 200 red, 350 white, 450 blue. So then the first step, take the observed counts minus the expected counts. So 210 minus 200 gives you 10. And then for white, 360 minus 350 gives you 10. And then for 430 minus 450, we get a negative. And the negative is okay in this difference because the next step is going to be squaring those. So if you take 10 in the red column and square it, it means you multiply it by itself. 10 times 10 is 100. So that's how we get the 100 here. And then for the white, again, 10 times itself is 100. And then for the blue, we have negative 20. But a negative times a negative will be a positive. So when we square negative 20, we get 400. So then step 3, take the result that I've boxed up there in each column, and now I have to divide by the expected count. So for the red, in step 3, we took 100 and we divided by the expected count for red, which was 200, and that gives us 0.5. For the white, we took what I boxed up, 100, and divided by the expected count in that column, that's 350. And when you divide 100 by 350, you get 0.2857, but notice they just rounded it to 2 decimal places, 0.29. They've rounded to 2 decimal places because you can see that our table is running out of room here. And then finally for blue, they took what was boxed up, 400, divided by what was expected, 450. So 400 divided by 450 gives you what they've rounded to, 0.89. So that's where those 3 numbers came from. So then the last step is adding those 3 up, and the chi-square value generated is 1.68. So here you could say for day 1, chi-squared is equal to 1.68. So we're going to do those exact same steps for the other 3 days. Number 7, compute the chi-square values for the other samples, days 2 through 4, by filling in the tables below. Compute the step 3 calculations to 3 decimal places, as shown in the previous example. They didn't quite do that, but we're going to do that for ours. So, day 2, the observed count, there they are, 200 red, 425 white, 375 blue. Then the expected counts, 200, 350, and 450. They did their subtractions, so 200 minus 200 for red is 0, 425 minus 350 is 75, and then 375 minus 450 is negative 75. Then they squared those results from step 1. 0 times 0 is 0. 75 times itself is 5625. Negative 75 times itself is also 5625. Now we need to do the step 3 calculations. So for white, we would have 5625, and then divided by its expected count for that column is 350. So 5625 divided by 350, and that gives us 16.071. And then for blue, we also have 5625, but remember the expected count is different. It's 450. So 5625 divided by 450, and that would give us 12.5. So then to get my chi-square value, I just add 0 plus 16.071 plus 12.5, and you would get 28.571, which you can see that they've written as 28.57, but we could put our 1 there if we want. So that's the chi-square value for day 2. So day 3, here's another table. We're just going to fill in some of these blanks. So we have our observed counts for red, white, and blue, expected counts for red, white, and blue. To find our step 1 value, we take what's observed, 180 minus 200. That will give us negative 20. For white, it would be 360 minus 350, which is 10. Then when I square for step 2, negative 20 times itself is 400. 10 times itself is 100. And so now for my step 3 values, for red, I would take 400 divided by 200. That's going to be 2. For white, I'm going to take 100 divided by 350. And that gives me 0.286. And then for blue, I take 100 and divide by the expected count there, 450, and I get 0.222. So then for my chi-square value, I need to add those 3 up. 2 plus 0.286 plus 0.222. And from that, I get 2.508. All right, so then finally, day 4 sample. Now we're just filling in a few more blanks on our own. So now we're just going to do step 1, take the observations, subtract what's expected. So for red, that would be 35. For white, that would be 5. And for blue, that would be negative 40. Then I have to square those results. 35 times itself is 1,225. For white, 5 times itself is 25. And for blue, negative 40 times itself. If you're doing this on your calculator, you need to type the parentheses first, then the negative, then 40, then close the parenthesis, and then press the squared button. And just remind yourself, you should get a positive, so 1,600. So then now getting my step 3 results using division. For red, that would be 1225 divided by 200. And that gives me 6.125. And then for white, that would be 25 divided by 350. And that gives me 0.71. Actually, sorry, 0.071. And then finally for blue, 1600 divided by 450. That gives me approximately 3.556. So this gives me 6.125 plus 0.071 plus 3.556. And if I add those up, I get 9.752. that's my chi-square value for day 4. So then number 8, which of the daily samples had the highest chi-square value? If we go through our previous answers, we'll see that the highest chi-square number came from day 2, 28.571. So day 2, that was chi-squared equal to 28.571. They also say, hint, first think about the size of the chi-square values for these 4 samples, okay? Then, do they appear to correspond in any way to the initial strength of evidence statements that you made when you circled the words strong, moderate, or weak in question 3? If you go back to what we did in question 3, remember that we said that day 2 had strong evidence. That was the one that had differences of 75 in the white and blue counts. Number 9. If the observed count and expected count are exactly the same for one category, is it still possible to have a large chi-square value generated by that sample? Did any of the samples in question 7 exhibit this behavior? So did we have any sample where the expected and observed counts were the same? We'll actually see that in day 2. The red observed and expected counts were the same. So in day 2, observed and expected red counts were the same. And we also noticed that we did have a large chi-square value. So they're asking, is it possible for this to happen? Yes, we saw that. Large chi-square value, and even when we had expected and observed counts being the same in one category. So now how about number 10? Now suppose that no category in a sample has an observed count and an expected count that are exactly the same. Is it still possible to have a small chi-square value generated by that sample? Did any of the samples in question 7 exhibit this behavior? So let's take a look at the small chi-square values. Day 3 was small. Day 1 was small. In fact, day 1 was the smallest. And if you notice, day 1, none of the observed counts are the same as what was expected. So the answer for number 10, that would be yes. Day 1 had the smallest chi-square value, and none of the observed counts were the same as what was expected. So then finally, number 11. In the day 2 data set, the actual counts for the white and blue categories differed from the expected count by 75 pieces. Which difference made a larger contribution to the size of the chi-square value? The difference of size 75 relative to an expected count of 350 white, or the difference of size 75 relative to an expected count of 450 blue? In other words, would a difference of 75 make a larger contribution to the size of the chi-square value for a category with an expected count of 350 than for a category with an expected count of 450? Explain your thinking. While we're thinking about that, the secret word for this lesson is serial. And if we go back to our chart for day 2, let's just take a look at what they're talking about here. Maybe just notice when we compare the white column with the blue column, we got 75 as the difference. There's also the same square, but which one gave us the larger number that we used in adding to get our chi-square value? The white column with 16.071. So going back to the reasoning for number 11, 75 out of 350, that's a larger proportion than 75 out of 450. So the actual counts for white, that made a larger contribution.